Welcome back, Chemistry 30. This is the MS3.1 General Characteristics of Organic Molecules section. So here, this is the start of MS3. So we'll be looking at what is the structure of organic molecules and describe why are they so stable. So if we take a look at this, organic chemistry, more than 16 million carbon-containing compounds are known. Chemists make thousands of new compounds every year, about 90% of which, so most of them, contain carbon in some way. And the study of molecules who contain carbon constitutes the branch of chemistry known as organic. So organic it's a little bit different from the grocery store term of organic. In the chemistry sense, it means it contains carbon. So the structure of organic molecules, since carbon has 4 valence electrons, so if we look over here at the periodic table, yes, it's group 4. It has 4 electrons, so it's going to want to share those 4 to get 4 more in a covalent bond. It has 4 valence electrons, therefore it could potentially form 4 bonds and virtually all of its compounds. When all 4 bonds are used, we have single bonds, and the electrons are it would make it a tetrahedral type shape, because sharing one, we can see it makes that nice tetrahedral shape that we're aware of. If I take one of those away and make a double bond, of course it would be trigonal planar, approximately 120, 120, and 120. So if I have one double bond, it'd be trigonal planar. And also what I could have is one single bond and one triple bond, and then you can see angles of 180. It would be a linear shape. So those are kind of the options for carbon bonded to other atoms. Almost every organic molecule contains CH bonds, so carbon's bonded to carbon and carbon's bonded to H. Because the valence shell of hydrogen can only hold 2, hydrogen only wants to share one to get one, to become like helium. Because yes, if we look over here, hydrogen is one valence electron. If it gains one more, it becomes like helium. So it only needs one more. So it's only going to bond somewhat on the surface of a molecule. So as a result, hydrogen atoms always are located on the surface of organic molecules, whereas carbon-carbon bonds tend to be the backbone or the skeleton of a molecule. For example, propane, which has 3 carbons, you can see carbons join with each other. They're kind of in the middle of the molecule because they can each bond to 4 different things, whereas hydrogen only bonds to 1 atom. So it tends to be on the outer surface, whereas carbon-carbon bonds tend to be on the inside. So if we look at the stability of organic substances, carbon forms strong bonds with a variety of elements, in particular H, hydrogen, oxygen, and nitrogen, and some of the halogen groups. So some of these ones over here in the halogen area, fluorine, chlorine, bromine, iodine, etc. Carbon, as I just mentioned, also has the exceptional ability to bond to itself, forming a variety of molecules that make up chains or rings of carbon atoms that we will see. And carbon has the ability to form really, really long chains that continue on for a long time. Now, carbon has an electronegativity of 2.5, and hydrogen has an electronegativity of 2.1, so it's around that 0.4. It's actually, if I was to look at our electronegativity chart, the difference is less than 0.4, and 0.4 was kind of that fringe number that distinguished a polar bond between a non-polar bond. So for the most part, it's going to be on the non-polar side. And due to symmetry, it's going to virtually be non-polar. So it's going to be a lack of polarity, virtually unreactive. The small polar bonds will tend to neutralize each other anyway. So even if I look at them as being a very small polar bond, due to the symmetry of the molecule, that tetrahedral shape, it'll neutralize each other anyway. Any other bonds not involving CC or CH are the ones that are areas of chemical reaction. So for example here, if I look at ethanol, there would be a set of electrons here that you could draw in, because oxygen. You can see this is going to be a bent shape area, whereas here we have a tetrahedral, kind of tetrahedral shapes there. and here we have a bent shape. So any reaction that's going to happen is going to be over here because this section is virtually non-polar. Whereas over here we have a dipole-dipole, and in particular, if we look here, look at that, hydrogen bonded to an O. We have hydrogen bonding there from our last section. So we do have a polar section of the molecule over on this side. That's likely going to be where the reaction is. So oxygen has electronegativity of around 3.5, so bonded with the carbon, which is 2.5, or hydrogen makes it fairly polar. Many reactions of ethanol involve the CO or the OH area. So the CO or the OH area, that area of the molecule. Whereas the hydrocarbon portion remains intact. So that virtually non-polar. And if we do consider it to be polar, it's very small, and the symmetry makes it overall non-polar. A group of atoms such as the COH group, which determines how an organic molecule will react or how it will function, is called a functional group. The functional group is the center of reactivity of an organic molecule. So if I look here, which bond is likely to be the center of reaction or the functional area? Again, we said that CC and CH are virtually unreactive. So when I have C bonded to something else, chances are that's where it is going to be. So in this case, likely C double bond end due to the largest, and if I look up the electronegativity in nitrogen and carbon, I would see that it would be larger than the 0.4, implying that that is going to be a polar area where chances are a reaction will happen due to a larger difference in electronegativity. All right, so you should be able to do the assignment. It's kind of just discussing what we just talked about. Should be able to run through that, and we'll see you again.